All right. So here we are. Just the day before the meteor struck the Earth, I think, is what it was. Right? And still, everyone showed up to class. That's very generous. But I guess today what I want to do, I'm just going to go back and I just picked a couple of, I guess, ideas that lead into concepts from the previous chapters to kind of discuss with you guys about to go through this kind of thing. And then on Wednesday we'll pick back up with the finishing up the rest of chapter 17, right? Because remember, we haven't finished chapter 17 yet. We ended basically at the end of the buffers titrations part there, right? So the stuff about solubility in KSPs is not part of this exam, although it's just more of the same anyway. But you know, it's there's plenty of stuff in there already, so we don't have to worry about finding more. Yeah, what's up?
What is on the exam in terms of that, like
15, 16, and up until where we got to in 17. So all the equilibrium stuff, basically. So anyway, so remember a couple of important details. Important detail number one, I didn't see any really issues with this last exam, but don't forget to bring the right kind of calculator with you guys for tomorrow, and what always goes along with that, and something I should have talked to you guys about last time, which make sure, I know some of you guys for some reason, you know like your graphing calculators or your like security blankets, right? But just make sure you guys know how to use the scientific calculators for the exam tomorrow, right? So make sure you guys can figure out where the log and the natural log buttons are. Those are going to be pretty important for tomorrow, right? And so and then you guys don't have to worry about that kind of stuff. The equation sheet's going to be there for you guys, although really, what is there, like 2 equations or 3 equations on this exam, right? The K expression and then the Henderson-Hasselbalch, and then relating KP and KC, right? So I think those are the 3 that kind of popped in mind. Although I might be missing one in there that's kind of eluding me at the moment. Let's see, kind of what else did I want to chat about, I guess. As we've become experienced with at this point, or as you guys hopefully have started to know, as much as I'm interested in that you guys can, string together equations to come up with a numerical answer for whatever, right? Always make sure, I'm going to ask you guys, why did you get to your answer, right? How did you get to your answer? I think there's quite a few of those questions on the exam, right? So make sure that you guys can explain, what does K mean, right? What information can we get out of it, right? Just because something's equal to 7, I mean, that's great. What does that tell you about the reaction, right? What does that imply, or how does that change, or what can we do with it? These kind of how and why type questions that come along with what we're doing here. Otherwise, it's just an exercise in, typing numbers into a calculator, right? Which doesn't really add any value to your guys' intelligence, right? So what does K tell us, right? That's what I'm interested in, right? How can we describe phenomena with it, right? That kind of thing. And I think for you guys, I know I mentioned this quite a bit, and there is a reason. For those of you guys who are going on into biochemistry, you guys will see K expressions all the time, right? That's one of the main methods is we have of figuring out how proteins and enzymes and all that stuff works, right? One of the first things we figure out is our equilibriums and our rates and all these kind of things that go along with that. And so extremely important in the realm of biological sciences. Let's see here. What else did I need to chat with you guys about? I think you guys right now we're in the same time, same place as we did last time. So I think you guys know that. I think that's kind of all that I needed to chat with you guys about. That comes to mind at least. So good, we picked an exam week. You guys are a little bit sleepier. Because you lost an hour of studying, Dr. H. We should delay the exam for an hour also to accommodate. No, I got you. Let's see. All right, so I think that's that. So like I said, I've just got a couple of questions for us to kind of work through and think through and kind of jog our memory a little bit about the earlier chapters, chapters 15 and chapters 15 and 16, since we're in chapter 17, so that was a little bit fresher there, hopefully. But yeah, okay, so let's get started with some prayer as we usually do, and then we'll go into it. Dear Lord, please let the meteor strike so we don't have to take the exam. Amen. All right, no, I'm just kidding. No, Lord, we just thank you for another blessing of another week. And we just thank you for another opportunity and another chance. And Lord, we know that there's going to be challenges in many different ways in this week, Lord. But just help us to humble ourselves and put those challenges before you, Lord. And help us to know when to ask for help, and help us to be receiving of help when somebody offers us a genuine expression of kindness in that way, Lord. Just help us not to be understanding that we're not alone in all this, Lord, and that we know that you're always walking beside us and in front of us, Lord. And so we just pray for your guidance, we pray for your protection this week, and we just pray for you to guide us on the path that you would have us set our feet on, Lord. And we just pray this in your name. Amen. All right. So, all right. Let's see here. Where do we want to start? Let's say that we have a reaction like this. Okay. We've got that and we've got that. Fantastic. What is the Kc of the reverse reaction? What's the Kc of the reverse reaction? The K of the reverse reaction. Those of you guys who've come up with an answer, what does this mean, right? What do these two values mean? What do they tell you about this particular reaction? Give it a little bit of thought. So what's the K of the reverse reaction, and what do those values tell you? Your brain doesn't work. Uh-oh. Okay, so first things first, if we have a value of K and we're asked what happens when we go in the opposite direction, how do we calculate that? Yeah.
Isn't it just 1 over K?
Yeah, we just take the inverse of it, right? So if you guys think about this, right, I'll emphasize this with the next question here, right? If you remember way back when life was much harder on exam 1, or excuse me, this was exam 3, 2, whatever, I forget now, that failed in my mind, okay. You guys remember that thing called Hess's Law back in Gen Chem 1? Yeah? They're like, yeah, sure, I'll nod, and I'll nod, otherwise he'll keep talking about it.
Wasn't that enthalpy or something?
Yeah, it's related with enthalpy and how we figure out the total enthalpy of a reaction, right? So if you remember back in Hess's law, we were, if we manipulate a reaction, if we reverse it, or we multiply it by 2, or divide it by 2, right, then we change value associated with that, right? So something similar going on here. If we reverse this reaction, we take the inverse of the K there, right? Does that make sense though? Why would it be the inverse? What is K?
Concentration of products over concentration.
Product over reactant. So if I flip something around, what is K? It's still what? Products over reactants, but the products and the reactants switch places. Got it? So how do you mathematically invert something? Well, you can multiply by -1 or do 1 over it. You guys with me on that one? So we're just following math, right? We're just following math with this one. Good? So not too bad, right? So I think, what was it, like 90 something for the, right? 90.09. All right, so let's call it 91 there or whatever, okay? Cool. All right, so what do these values tell us? So the Kc of the forward reaction is equal to that. And then we'll just call it, Kr for the reverse, although that doesn't mean anything, right? Is equal to 91, right? So what do these numbers tell us? Yep.
There's more PCl5 products.
Right? So we have a relatively small Kc, right? 0.0, what is it, 0.001 or 0.01, right? Which means we have more of our reactants of our product. We have more of the stuff on the left than on the right. Okay, and that's emphasized by when we do the reverse, right? We have a pretty big K if we do the reverse reaction, which means that the PCl5 side there is favored, right? That's easy stuff, right? That's easy, Dr. H. I knew that a couple weeks ago, right? But make sure you guys can explain it to me, right? That's in that, yeah.
Can you back up like 1 minute?
Sure.
Sorry. So, in both instances, PCl5 is favored. So we're not comparing the two Ks.
Directly to each other?
Yeah.
Not necessarily, right?
Okay.
They both point to the same conclusion though, right? Because they're telling us, depending on which way we look at it, which reaction, right? The forward or the reverse, right? It tells us about which side is favored.
Yeah.
So if you, I guess the other way of, I shouldn't skim on this stuff, I suppose. Right? Remember this here is just showing us, right, that reaction there.
Okay, so at what point can we consider numbers small?
Usually if it's less than 1, right, it's kind of the definition there, right? Well, I wouldn't say definition, the point that we conclude that, right?
Okay.
Okay, I feel I didn't answer your question, but what were you really trying to ask?
Isn't Kc less than 1?
Yeah, okay, 1 times 10 to the 9 is 2, right?
But we can still consider that large.
No, I didn't say that one was large, that one's small. The 91 we would consider large.
Okay, I'm sorry.
No, that's
My
okay.
bad.
Yeah. We good now?
Yeah.
Okay, cool. All right. So the question along the same lines here then. Let's see. So if we have this, oops, that's not parentheses. Right? And let's just say we have some kind of Kp value for that, right? Okay, so let's just give it an arbitrary, nicer here, right? Let's say that Kp is equal to whatever, x, right, just some value. So what would Kp be for then if we do this?
coefficient there, Doug, or am I in it?
Yeah, no, I did, I forgot my green for the IT. Thank you very much. Perfect.
Can stoichiometry be reduced or does it not matter here?
It can, right, but I'm just saying what happens if we do this, right? Yeah. What happens to our expression of K? So we gotta think about this one, be careful. Right? Just think about where do your stoichiometric coefficients go in your expression of K. That's what this question is asking, right? This question isn't just asking, can you multiply things by 3? It's saying, do you understand where the stoichiometric coefficients go in K? Is everybody with me on this one? Yep. So where do your stoichiometric coefficients go when you're expressing a value of K? It's concentration of products over reactants, we got that. But the products and reactants are raised to their coefficients. And what did we do to the coefficients essentially? We multiplied our coefficients by 3, so that means what is our expression of K then? It is cubed, right? Everybody with me on that one? So this is a clever way of me asking, hey, are you thinking about what K means and how we express it and how we set it up? Got it? It's no different than what we did on the previous one where we, why did we invert? Well, we flipped everything around, right? With me on that one? Did I trick you on it? I'm sorry.
I have a drainage resistance.
It's all good, it's all good. Like I said, now it's good to miss them here. Why?
So we don't miss them later?
Yep. Okie dokie.
Wait, it's a quick question.
Yep.
So, you're saying it's constant, but only insofar as its own, not even its own reaction?
No, it's always a constant, right? We're just talking about how did this is a question basically asking where does the stoichiometry come into play, right? That's what it's asking. All right, so another little thinking question here. Actually, I gotta give you a math question here first. So, if we have this, if I give you KC, calculate KP for me.
Do we assume the temperature?
Yeah, the temperature is constant, right? I'm not changing it in between. Right?
If that's it. Oh, sorry, I didn't read that you.
Oh, it's okay.
close enough? Are we talking decimal places or whole numbers?
I wouldn't say close enough, but you're off by whole numbers.
I guess, I'm just having a little bit of a.
You don't understand, Dr. Hayes, I'm very insecure. You're all good, you're fine.
It's not good.
All right, so first things first, what do we need to do? So first thing we need to know.
How to convert KC to KP.
How can we relate KP and KC, right?
KP equals KC times RT to the raised to the
Right.
change.
So we have an equation for it. Right? KP is equal to, right, KC times RT, and then this delta N up there, right? Great, now what's the second thing we need to know?
N,
Before that,
R,
before that. We need to know what in the world those things even mean, right? So you guys are right, we need to know what KC is, we need to know what R is, we need to know what T is, and we need to know what delta N is. Otherwise we just have a alphabet soup, right? There's a bunch of things in our spoon and we don't know what they mean. You guys with me on this? And we have an equation that's got 1, 2, 3, 4, 5 things in it. So we need to be able to identify those 5 things. Okay, well, K's are K's, those are equilibrium expressions, right? I have to give you information about one or the other, right? Either KP or KC, okay? Well, good thing we have KC, right? So we got information about that. R is what?
0.8.
8.314.
No, 0.8.
0.826.
Yeah, yeah, 206.
Ooh,
They're
okay.
both correct.
All right.
In this case, we want the
Interesting.
one that deals with the ideal rate law, which is 0.08206.
So R is our gas constant, okay? There are a couple different gas constants. We're dealing with units of concentration, so our R better deal with units of concentration, right? You guys with me on this? Paying attention to units, very important, okay? The 0.08206, that's the one that deals with concentration, right? Because it's in liters, atmospheres, mole, Kelvin, right? So we can take care of the concentration issue with that. Do we have temperature? Yeah. What's important to pay attention to here? Why is it important to pay attention that it's in Kelvin?
Because you might give it to us in Celsius to trick us.
No, I'm giving it to you in Celsius, right? Because we understand that whenever we're dealing with gas constants, it's always got to be in units of Kelvin. Got it? But it's just an exercise in are you paying attention to the most important thing I can teach you guys ever, which is what? Pay attention to units, okay? All of our gas constants, no matter what the value they are that I give to you guys, is in units of Kelvin. So make sure that you have temperature in units of Kelvin, okay? Okay, so equilibriums, constant, temperature, delta N is what? Change in moles of our reaction, got it? So what is our delta N in this case? Well, the change in something is always the final minus the initial, right? What do we have in our products?
3 moles.
Minus what's in our reactants here, right? So we have 3 minus 2, that is equal to our delta N. Got it? So in this case, good stuff, it's just equal to 1, right? So then we can just plug everything in. We have our value for KP, we have our value for KC, we have our value for delta N, and so I got KP is equal to about 0.335 or 5, correct? No, I can't read my own handwriting.
348,
348, is that what you guys got?
which would kind of be 338, or 335.
Okay, I'll just say 0.34. Sorry, I can't read my handwriting for some reason. But that seems about right. Good?
Are the R values on the program sheet?
Yeah, I will always give you that stuff. Yeah, constants I will give you guys. Okay. All right, so this is one of these equations that we haven't really used since chapter 15, right? But now we've got a nice refresher over here in case we need to relate KP and KC, right? All right, so question for you then, related to this, something to think about, right? It's always more fun to think about things than do math. Okay, wait a minute, Dr. H, you gotta do both, right?
It's too early to do either. Out of curiosity, are the OChem classes also obscenely early?
I don't think 8 a.m. is obscenely early. When would Kp be equal to Kc? Good mathematical question. What's up? What conditions need to be met for Kp to be equal to Kc? So hang on a second. Think about it just a bit. Or did you have a question or two?
No,
Okay, so hang on to the answer for just a second. Was that always there and just didn't notice?
It's been like that
Oh,
for
okay.
years.
Oh, for years?
Yeah, I think so.
That's a long-lasting diet. Goodness.
No, I mean,
I know, I
Yeah, I did put some new colors in and it was a horrible choice.
don't think it's a horrible choice. It's a choice, right? It's your choice, that's good. What's up? So you had an answer for me. So when would Kp be equal to Kc?
when the moles are equal on both sides, because then delta N would be 0.
And if delta M is 0, then R times T to the 0 is equal to what?
1.
1, and so then what happens? Kp is equal to Kc. Got it? All right. Where do we get this expression from to begin with, the Kp related to Kc? How do we even derive that to begin with?
I don't know.
Ideal gas law.
Hmm?
Ideal gas law.
From the ideal gas law, remember, we can relate concentration to pressure, right? If we rearrange PV equals nRT, we can relate pressure and concentration, right? And that's what we're doing here, right? Kc is an expression of equilibrium in concentration. Kp is an expression in pressure. Got it?
Newton or Leibniz for it. It seems like they're responsible for
Can we
everything.
blame people for constants of the universe? Sure. Knock yourself out. I'll show you, God. Right. Yep, okay. So we have that equation. Got a couple of questions for you here.
Oh, no.
So what happens, right? When more O2 is added, right? How does our equilibrium shift? NO gas is removed. Increased pressure will decrease volume. be careful when you answer something like that. I just talk about which direction does it go, right, to the left or to the right, that kind of thing.
Yeah.
I know what you're saying, but just be, right, just, like for this, that doesn't make sense, right?
So just right, left, or right?
Yeah, basically, yeah, yeah.
Drill sergeant chance.
I mean, you could say forward and reverse them too, right, and you can give yourself driving directions.
In 100 moles, turn.
Sounds good to me. I like the metric system, very logical for me. Multiply by 10, all good. All right, so first things first, kind of, you know, put the brain into the right gear, so to speak. So we have a question where we're given some reaction, and then we stress that equilibrium, right? So whenever we're dealing with stressing and equilibrium, we're always working with
QC?
Q and C, right? Okay, we have Q and K, right? Those are always, that's how we mathematically could figure this stuff out, right? And Q and K are related to which principle? Le Chatelier's principle, right? So whenever something is talking about stressing a system, or something is removed, or changing an equilibrium, right? This kind of stuff, we're talking about K, we're talking about Le Chatelier's principle, okay? So when we're dealing with the principle side of things, we're just saying qualitatively what happens to this reaction, right? Which side does the equilibrium shift towards, okay? And then somebody said the Q and the K, right? So we could mathematically do the same thing by giving you guys values, calculating Q, and comparing it to K. You guys remember about Q and K? Right? Okay, so what happens if we add more oxygen? What's going to happen to the system? Which side is it going to go towards? To the right, okay? Can you guys explain why?
Because if you have more matter on one side of the equilibrium, it pushes it the other way or something.
So that's an interesting thought, right? So if I add more stuff on the left-hand side there, right? Remember, for a reaction to happen, two of these molecules have to smack into each other for the reaction to happen, right? That's collision theory, yes? So if I put more of one of those in there, it increases my chances of the reaction happening, and so I could push it to the right, right? That's one way of thinking about it, right? A conceptual way, a good way of thinking about it. I like it. What's a mathematical way of thinking about this? What happens if I put more on one side of this equation? K doesn't change, right? The position in the equilibrium might change, yeah.
The probability for more product to be made decreases because you have more reacted.
Right, that's what we were talking about there at the beginning, right? So we have this collision theory thing going on. So K is a constant, right? Our assumption is that temperature remains constant in these cases. Yes? So K is constant. So we stress the system, and what has to happen? We have to establish new concentrations, right, for everything that's in there to reform our K. So we're saying we can change one side of it, but the answer is always going to be the same, right? You guys with me on this? Yeah.
So then why in that last, or a couple questions ago, would K be tripled?
Because again, we're talking about where does the stoichiometry go with this, right? For these particular conditions.
Right now, we're talking about changing the concentration of the stoichiometry of the equation.
So, then NO, nitrogen monoxide, is removed, right? So if we get rid of some NO, right, what happens to our system? Which way is it going to shift?
It gets more positive because it's not being told no all the time.
Yep. Which way does it shift?
Less.
Shifts to the left, right? If we remove something, the equilibrium shifts to make up that missing portion. If we add something, it shifts away from where we add it. Alright, you guys with me on that? What happens if we increase pressure? If we increase pressure, yeah.
If we increase pressure, then whichever side of the equation has the fewest moles is gonna be favored.
Fewest moles of,
Of like total stuff.
okay.
So, like, the left side has 3 moles in stoichiometry, the right side only has 2.
Right, so if we're increasing pressure, right, it'd be if I asked you guys all in this classroom to come sit in the front row, right? And so we're gonna start banging into each other here, you guys wanna spread out, right? If we increase pressure, we go favor the side that has less of the gas in there, right? To relieve some of the pressure, if you wanna think about it that way, right? What happens if we decrease volume?
We're increasing pressure.
We're increasing pressure, right? Those are the same. Remember, the relationship between pressure and volume are inverse. Right? If I increase pressure, I decrease volume. If I increase volume, I decrease pressure, right? So they're asking the same question, just from a different approach. Yep.
Question for the pressure.
Huh?
For the pressure,
Yep.
then, what if both sides have the same amount of moles?
Great question. What happens if both sides have the same number of moles?
Nothing happens.
Nothing's gonna happen in that case. Because remember, we're just forcing everything together, and if we, so another way of thinking about it is if we push, by increasing pressure, if we push the NO and the O2 together, they're going to be more likely to make NO2, right? So if you wanna think about it, but then if we have equal moles on both sides, everything's gonna get squished together more, and then it's not going to change anything. Good question, yeah?
If you decrease volume, you increase pressure? Also,
It's gas.
The relationship of pressure and volume are inverse, right?
okay.
So if you think about this, right, if we assume everything else is constant, right, in terms of how much of the stuff we have in there, decreasing volume is smushing things together,
Okay,
right?
yeah, that makes sense.
Like a hydraulic press.
So I didn't ask the question on here, but we did talk about it in class, right? It's an idea that we talked about in the first semester of Gen Chem, right? If we have exothermic or endothermic, right? If heat is part of our reaction, right? If heat is part of our reaction, then we could talk about what happens as we add or remove energy from the system there, right? If we cool it down or heat it up.
If it's exothermic, then adding in heat is gonna make it shift to the left, and like cooling it down would make it shift towards products.
If it's exothermic, yeah. But we have to be careful when we ask questions like that, right? Because what changes when we increase or decrease temperature?
Entropy.
Okay.
Our K does, right? Remember, K is constant at a temperature, right? At a specific temperature, right? So if we start to do this, then it gets a little bit more complex there, but the idea is okay for us. Okay? We're not an engineering course here. All right. Ready to shift gears a little bit?
Are we shifting gears in order, or are we just skipping them?
Okay. So, write the balanced reaction. Of phosphoric acid and magnesium hydroxide. Write the balanced reaction. We mix phosphoric acid with magnesium hydroxide. Let's see if I can improve my script here for this thing. So that's phosphoric. So, what, I'll talk about this in just a second, but these are gonna completely react together.
Oh.
Okay.
What is that? What's the trunk?
Alright, so first tricky thing to pay attention to is how to name these things, yes? So when we're naming our acids, our oxyacids, particularly, right, remember, it's the adic itis, right? So the relationship of the name of the acid and its conjugate base, right, is the H and the X and the ites and the us. So phosphoric acid comes from phosphate, right? So what is phosphate? PO4,
Frick.
right? PO4 with what?
A -3 charge.
3 minus, one of the most important polyatomic ions. One of the most important polyatomic ions, phosphate. PO4, 3 minus. If I have a 3 minus charge, how many H pluses can I carry?
3.
You guys with me on this? So why is it so important to know our polyatomics?
So
We
we
can
don't
use it to predict the acids and the bases and the, is it polyprotic, is it monoprotic, all this kind of stuff that goes with it. Got it? You guys will see your polyatomics every single class that you guys have with me, right? And then when you even get to finally get rid of me, you'll still see them then anyway, okay? So they are everywhere in chemistry. That's why I say, hey, just go ahead and memorize these. You're gonna see them, you're gonna need to know their charges, their composition, all this kind of stuff, okay? So if I have a PO4 3 minus from phosphate, right, that means I have H3PO4 as an acid. Got it? Okay, then we got magnesium hydroxide. So it's just this, right?
No,
No, I don't make mistakes.
magnesium is an alkali earth metal.
Alkali earth, a group 2. Magnesium always has what charge?
-2, or +2.
Plus 2. Hydroxide is always -1, right? So magnesium hydroxide has 2 OHs. Got it? Now we can put these together. Although, let's back up for just a second here and just kind of think about this a little bit. What do we know about H3PO4, phosphoric acid? It is one of our weaker acids, right? What do we know about magnesium hydroxide though? It is a strong base, okay?
If they would totally neutralize?
Absolutely they will. I'm not asking you guys what's the pH at the end of this,
Okay.
right? Strong bases are gonna react with weak acids, right? They're going to go after all of the H's that they can. That's their goal in life, right? You guys with me on this? It would be a different question if I said, hey, what if we have a weak base and a weak acid? Right? We'd have to do some completely different kind of assessment for that, right? Well, not completely different, but I'd have to ask it in a different way. So everybody with me on this important idea here, right? Identifying strong acids, strong bases, and weak bases. If you have a strong around, it's going to react, whether it's strong acid or strong base. Everybody with me on this very idea here? Yes? What's up? I don't know who raised their hand first.
For the bases, okay, so you have like the 6 strong or 7
Yep.
strong or whatever. So you know anything that's not one of those is weak, pretty much.
Correct.
But for the bases, is there like?
If you see hydroxide around, it's a very safe assumption to make it's a strong
Oh,
base.
okay.
Yeah, that's really all it comes down to.
Okay.
There are exceptions and differences, but we have to address those a little bit differently. For our purposes here, you see hydroxide, assume it's strong. What's up?
So I was surprised to hear you say that the strong base is reacting with the weak acid will completely.
A weak acid is still an acid. A strong base is a strong base, right?
So-
Now, your question that I think you're maybe, and I'm sorry, I probably shouldn't have cut you off there, but, you know, how do we know when is enough to react,
Yeah.
right? So there we go into the next part of the question that we'll talk about here, right? Which side is favored for the reaction, right?
Okay,
So
so
that's a good question.
just like big picture, what's the difference, what's like a telltale difference between a strong acid and strong base versus a strong base or acid reacting with a weak ace or base?
It's, for our purpose, for this type of question, nothing.
Okay,
We'll assume that the reaction happens,
okay,
right? And then if I came up and said which side is favored,
yeah,
or what would the magnitude of K be or something like that, then we'd have to go and have some kind of approach to it there, depending on whether it's strong or weak, right? So here I'm just saying, hey, just write me the balance equation or reaction, and we can assume that's all going to happen, right?
Okay.
Great question though. Yeah, looks good. All right. So acid plus base always goes to make, our salt, I'll write it down here, and water, right? That's how a neutralization reaction works. The OH from here, right, reacts with one of the H's from here to make water, H2O, right? So where does our salt come from? Well, if it's not the OH's and the H's, it's gotta be what? The magnesium and the phosphate, it's whatever else is left over. Got it? Right? So, and there's where it's important, right, to know your charges. Mg, 2 plus, PO4, 3 minus, right? So we just drop the coefficients down, right? Or the charges, so Mg, 3, I don't know why I put that in parentheses, PO4, 2, right?
You just gave away the next bit.
Did I?
Yeah.
What's the next bit? Oh, well, yeah. Good, so now we have our equation, but it's not balanced, okay? Gotta balance this. So 2 here, 3 here, and 6 of those, right? Good? All right, so a thought then. How does this reaction proceed? Oh, yeah, what's up?
I was just gonna ask, am I right to say that it would be very unlikely for this to happen, because,
Well, it's extremely likely for this to happen.
oh, I remember seeing that for each hydrogen that comes off of there, it being like, many hydrogens, it's harder and harder to take another
Why?
hydrogen off. Cause it's a -3 charge.
Well, we'll end up at -3, right?
Yeah,
So that's it. Here's a good question to build off of Andrew's ideas there, right? So we have a polyprotic acid, right? We have H3PO4. So the way we write this out, it's perfectly fine, except there's nothing wrong with that. But how does this reaction proceed? This reaction doesn't proceed by 3 of these instantaneously finding 2 of those, right? And everything goes on, right? There's these subsequent acid-base steps that happen, right? One acid-base reaction happens, the next one happens, right? The next one happens. Right, so there's an example that we did, I believe it was, the week of spring break, maybe?
I'm sorry, we did something the week of spring break?
Yeah, we have class, right?
We didn't have class during spring break.
The week before, sorry.
Oh, okay.
Sorry, right? So, remember, when we're talking about these polyprotic acids, there are subsequent acid-base steps that happen. Okay, here's what I mean. Right, so if you take a look at the data for H3O+, right? Whoops, not H3O+, pardon me, H3PO4, right? Right, and we'd have a Ka value associated with that. right, for the first dissociation, right, for the first dissociation of phosphoric acid. You guys with me on this? The first proton that's lost, okay? Then if you look it up, it'll have the next one somewhere down the list. Right? Until we finally end up at the end, and good. So what does this tell us? When you have polyprotic acids, you need to handle each of these acid-base steps individually if we're starting to ask about the Ks and the equilibrium concentrations and that kind of stuff, right? Each of these has a K dissociation value associated with it, okay? What else do these Ks tell us? Well, -3, -8, -13. What does this tell us about the dissociation at each of these steps?
It's harder.
It gets harder and harder. Does that make sense? What's going on in each of these steps here? Right? What did I kind of leave off of this side of the equation over there? Right? You guys with me on this? Why would it be harder for each of these subsequent dissociations to happen? Yep.
Because PO4 is getting like more of a negative, so it just wants to hold on to it.
Right? We're trying to separate negatives and positives. The bigger the negative, the harder it is to pull a positive away from it, right? That's what it comes down to. Let's think about this in the other direction. Here are our Kas. What does this tell us about the strength of the bases? Here we have a really, really, really weak acid, right? Something comes in at -13. Barely a stronger acid than water, right? What's the Ka for water?
1.8 times, or 10 to the 14. So
Yeah,
90.
basically, right? Although we have to be careful with that too. But, well, for our purposes, we'll say times 10 to the -14. Okay? So water is just barely a weaker acid than this is. So what does this tell you about the base here?
It's very
Weak acids make
it's very strong.
stronger bases. Right? And this could lead us into that whole discussion that we talked about with buffers there. Right? That's why buffers work. That's why we have to have the equations present that we use for buffers. That's why you have to set up the ice tables and all this kind of stuff with it. Weaker acids make stronger bases. I'm not saying strong bases in the hydroxide sense, right? I'm saying stronger. Strong enough in the sense that we have to develop K expressions for them, right? But strong acids do what? Make weak bases, right? We can't make a buffer with HCl, right? You can't make a buffer with HCl. Why? What's the definition of a buffer?
A weak conjugate acid base pair.
Right? Weak acid with its conjugate base in solution, right? And so the question would be, why do we need both of those in there? Right? What's the purpose of a buffer is another way of asking this.
To take some of the reaction away from the strong acid or base.
Well, to maintain a pH, right? To mitigate large changes in pH, right? You guys with me on this?
Hopefully.
All right. So there's a little bit of a review there from 15 and 16. Remember, this leads into 17 also with our titrations and buffers and all that kind of stuff there, right? I'll be around today. If you guys need a hand, just drop me an email or swing by the office. And I will see you guys tomorrow. Okay? See you guys. Yep.